We have now derived numerical approximations that allow us to update the flow field in time in the interior of the domain. Before we can do a specific problem, we need to include boundary conditions. The boundary condition can vary from problem to problem, but here we will focus on walls with given tangential and normal velocities. We often take these velocities to be zero over most of the boundary, representing no-slip rigid walls. In our case, the boundaries are straight lines connected at the corners to enclose a rectangular domain with no in or outflow. Thus, the normal velocity is zero for all the boundaries, meaning that the u velocities are zero on the left and right boundary and the v velocities are zero at the top and bottom. The tangent boundaries are, however, allowed to move and induce a flow in the domain. Thus, we specify the tangent velocity at each boundary, setting one or more to a non-zero value. The tangent boundary velocity is specified using the ghost points. When we use a staggered grid, the normal velocities are specified directly on the boundary. The tangent velocities are, however, not. To enforce the correct tangent boundary condition, we need to use the ghost points and set the tangent velocity at the ghost points to the correct value. The velocity at the wall can be found by linear interpolation, assuming that the ghost velocity is known. Since the boundary is midway between the center of the ghost cell and the first cell inside the domain, it is simply the average. The unknown velocity is, however, the ghost velocity, while the wall velocity is known, so we solve for it and find that the ghost velocity is equal to twice the wall velocity minus the velocity in the first interior cell. Obviously, if the wall velocity is zero, the ghost velocity is simply the negative of the first interior velocity. Thus, once the velocities in the interior have been found, we set the ghost velocity to allow us to take the next time step. Here we have assumed that we are working with the bottom boundary. Obviously, the derivation for the other boundaries is essentially the same. In the problem that we will do at the end of this lecture, we will be assuming zero flow through the boundary or zero normal velocity. However, zero normal velocity is a special case of a given normal velocity, and since we can allow for arbitrary normal velocities without any additional complexity, we will do so here. Consider the control volume in the figure, where there is a given normal inflow ub through the boundary on the left. Since the velocity through the boundary is known, we can modify the incompressibility conditions, including ub. The pressure equation is then derived in the usual way by replacing the unknown velocities in the incompressibility condition with the expression for the corrected velocity, stating that the corrected or final velocities are the predicted velocities plus the discrete pressure gradient. However, since ub is known, there is no need to replace it, and the resulting pressure equation therefore does not include the pressure to the left of pi, j, and in the divergence of the predicted velocities, we replace the predicted velocity at I minus a half, j by ub. This is actually a rather remarkable result, since we do not have to worry about the boundary conditions for the pressure at all. While the pressure boundary condition deserves further discussion, we will not do so here in the interest of moving on with the development of our code. The pressure boundary conditions can be implemented in many ways, and the most rigorous way is to rewrite the equations for the pressure points next to the boundary, setting the appropriate terms to zero. Doing this does not require any ghost points. Here we do, however, use a simpler approach and set the density in the ghost cells equal to a large value. Since we divide by the densities, this would result in these terms being zero if the density was truly infinitely high. While we do not use an infinitely high value for the density, we can nevertheless make the blue terms very small by a sufficiently high value. The predicted normal velocity at the wall, v at I, j minus a half, or the purple term in our example, also needs to be set to the correct inflow velocity. For methods with sharp interfaces between fluids of different densities, the advection of the sharp interface is the major challenge. We will introduce a method to track the interface in the next lecture, but here we simply assume that the density is updated using the equation stating that the density of a material particle is constant. The equation stating that the density of a material point is constant says that the time derivative of the density plus the velocity times the density gradient is equal to zero. This equation can be rewritten slightly using that the flow is incompressible to pull the velocity under the divergence. While there are a number of schemes that allow us to write down a stable discrete equation for the advection equation, the simple forward in time centered in space scheme used for the Navier-Stokes equation is unconditionally unstable. To be able to use it, we add a diffusive term to the equation, taking the diffusion coefficient equal to the fluid viscosity so that the allowable time step is the same. The new density at the pressure point is therefore the old density minus delta T times the outflow of mass through the right and top boundaries minus the inflow through the left and the bottom boundaries, plus the viscosity times delta T times a discrete approximation to the second derivative. We note again that this is a temporary way to update the density so that we can code up the FlowSolver. The code snippet for updating the density is a straightforward coding up of the discretization on the last slide. We loop over all the interior points, with I going from 2 to nx plus 1 and j from 2 to ny plus 1, computing the right-hand side using the old values of the density. We are now ready to pull all the pieces together and write a complete FlowSolver capable of simulating flow driven by differences in density. First, we review the steps or the solution strategy. We start setting the velocity at the ghost point and finding the density at the new step using the simple and temporary advection diffusion equation approach just described. Then we find the predicted velocity. We then solve the pressure equation, and once we have the pressure, we can correct the new velocity field. Once we have the new velocity field, we are ready to take the next time step. It is sometimes helpful to represent the steps in a slightly different way, and on this slide we show a simple flowchart on the left and a pseudocode on the right. In both cases, the steps are the same as on the previous slide. We set the ghost velocities, advect the density, find the predicted velocity, solve for the pressure, and correct the velocity. The full code is available as a download, but since it's only about 100 lines, we'll go through the listing on the next slide. Remember though that although this is a complete and working Navier-Stokes solver, it's a very elementary one. Since it's only first order in time, we advect the density in a very rudimentary way, and we take the viscosity to be the same everywhere. The full code is shown here in sufficiently small font so that it fits into 2 columns. After the header, we set the various parameters that define the problem and the numerical solution. Then we define the various arrays and set them to 0. The initial density distribution, defining the drop, is set in the light yellow box. Most of the code consists of the time loop, which is shown with a gray background. Inside the time loop, we first enforce the tangential velocities at the boundaries by setting the ghost points in the pinkish box. Then we advect the density. The predicted velocities are computed in the light brown box at the bottom of the first column and the top of the second column. In the light blue box, the pressure equation is solved and the velocities are corrected in the dark pink or light red box. The final thing is the plotting done in the green box. Notice that since we are using a staggered grid, we need to find the velocity at a common point before doing a quiver plot. To get velocities at points that start on the boundary, we average ui, j and ui, j plus 1 and vi, j and vi plus 1, j to get velocities at the corner of the pressure controlled volumes. The last pause statement ensures that the solution is plotted in every step. We note that we plot the solution at the end of the time loop, so the first frame is after 1 time step. We could obviously also plot at the beginning of the loop, but then we would take 1 extra step at the end. Since our method is explicit, the size of the time step must be small enough so that this method remains stable. We will not discuss the stability here, but simply quote the results. Those limits are derived for first order in time and second order centered in space discretizations of the linear advection diffusion equation, but have been found to apply to the same approximation of the Navier-Stokes equations. As implemented, the method is subject to 2 stability constraints. The first comes from the diffusion part and says that the viscosity times the size of the time step divided by the density and the grid size squared must be less than 1/4. The second limitation comes from the fact that the current scheme is unstable for the inviscid case, and the viscosity must be sufficiently large to stabilize the scheme. Thus, the maximum velocity squared times density and delta t divided by the viscosity must be less than 2. To test our code, we use it to simulate the fall of a circular drop in a square domain. It is important to start with a simple problem that is easily solved, so we take the density of the drop to be only twice that of the ambient fluid. The tangent velocities at the walls are 0, explicitly set by specifying u north and so on, and the normal velocities are also 0 since the velocity field is initially set to 0 and the boundary points are not updated. The drop has a radius of 0.15 and is initially located at x equal to 0.5 and y equal to 0.7. The grid is 32 times 32 pressure cells, and we follow the evolution for 100 time steps, taking dt equal to 0.00125, determined by trial and error. The code is easily run interactively so that the evolution of the solution can be seen. Here, however, we just show a contour plot of the density and the velocity field after one time step and after 100 steps at time 0.125 on the left. Because of the coarse grid, the initial shape of the drop is somewhat jagged. As the drop falls, it deforms, becoming flatter with the back caving in, and it also quickly becomes a smooth blob instead of a drop with a sharp boundary. The density at the final time is shown in the top frame on the right-hand side, and in the bottom frame we show what it should look like. It is clear that even though it is only fell a short distance, the present code does a terribly bad job at affecting the density, and we need a better approach. It is true that we did add diffusion, but as discussed in the next lecture, direct advection of the density requires either a low-order method with a similar level of diffusion or a higher-order method that produces oscillatory or wiggly solutions. A different strategy for updating the density is therefore needed.